The recording.
Okay, we're on the record.
Okay, welcome everybody to this week's colloquium. So today we're especially happy to have Yi-Zen Chu, and we're especially happy because Yi-Zen is an alumnus of CASE. So we've had many successful alumni, and we're always happy when they're able to return and tell us what they've done. So Yi-Zen got his PhD here in 2010. He then went on to do postdocs at Arizona State and the University of Pennsylvania and the University of Minnesota in Duluth. And then since 2017, he's been a professor at National Central University in Taiwan. And he's going to tell us today about why light does not always travel on the light cone.
Thank you. Thanks for inviting me. Always good to be back at CASE, even if it's just virtually. Hopefully, everyone is keeping safe, and not too long in the future, I'll get to actually visit in person. So today, as the title suggests, I'm going to tell you one key property of both electromagnetic and gravitational radiation, which is that even though we like to think of the associated particles, the photon and the graviton, as massless, it turns out that they do not, in fact, propagate strictly on the light cone in all circumstances. So what we'll see is that in curved spacetimes and also in odd dimensional spacetimes, I will show you explicitly how they also travel inside the light cone. So there's some nomenclature here. When these fields travel inside the light cone, sometimes people say that this is a violation of Huygens principle. And this part that travels inside the light cone is usually dubbed the tail. So how did it all begin? So it came down to a mathematician named Hadamard. I think this is almost 100 years ago now that he gave a set of lectures, first describing his research into the math of partial differential equations. And what he showed that was that in what we would call curved space-time, the Green's functions of the associated wave operators would not only be non-zero on the light cone, but also inside the light cone. But it took a while before this knowledge propagated into the physics community. And it was thanks to actually Bryce DeWitt and Robert Brahmi, who was, I believe, was Bryce DeWitt's first graduate student. It was them together who brought this knowledge of the tail phenomenon into the physics community. So in this paper that I'm citing over here, they showed how electromagnetic charges in a curved space-time would produce a signal, and this is the term, the final term in the equation 5.26, that basically is history dependent. I'll show a picture in a little bit. And this gives you a novel cell force on your electromagnetic system that has no counterpart, at least in four-dimensional flat space-time. There was also a follow-up work by Hobbes, who used a slightly different formalism to do the same calculation. I just want to highlight that Bryce DeWitt has a sort of an autobiographical memoir, probably written by Cecil DeWitt, actually. But there inside, you can find a tribute to his first student, where he tells us that he owes quite a bit of intellectual debt because it was through his project that he read Hadamard's book and learned a lot about the properties of Green's functions in curved spacetimes. So what's a Green's function? What's it all about? Let me begin in the simplest context, namely in four-dimensional flat spacetime, before we go on to do the curved case. So in four-dimensional flat space, the wave operator is just two time derivatives minus a Laplacian acting on your field, which in my case, I'll just assume for simplicity is a massless scalar. And J here is just the source that is responsible for producing the phi field itself. Now, if you want to solve a system like that, the first thing to do is to, in fact, solve for the Green's function of the wave operator, which I like to always think about conceptually as the field. So the Green's function always depends on 2 points, which I like to call x and x prime. And x is the point where you're observing the field, whereas x prime is the location of the point, the space-time point source that's responsible for the field itself. And the way to see this is that in the wave equation for G itself, if you compare that with the equation for the scalar, you see that the delta function on the right-hand side of the Green's function equation is telling you that J, the source of the field here, is just a point in space-time. That's why it's a delta function. And so the physical field itself, phi, is nothing but the superposition of the field produced by all space-time points, but weighted by the physical source J. And let's see what the actual solution is for in 4 dimensions. What you see here is G is now is a delta function in the elapsed time. T is the observer time, T prime is the emission time, and x minus x prime is really just how far the observer is away from the source. And this tells you in turn, because the delta function is non-zero only when the argument is 0, that tells you that the elapsed time is equal to the distance in units where c is 1. And in other words, that just tells you that in 4 dimensions, massless particles do in fact propagate only strictly on the light cone. And moreover, you can see that there's a 1 over distance multiplied to that delta function. And so that tells you also that the amplitude of the wave in 4 dimensions fall off with 1 over the distance between source and observer. So to some of you, these things could well be extremely familiar, but I highlight these basic properties because I will show you in a few slides. These are actually not universal properties. In particular, when you do cosmology and you look at the tail signal, these fall-off properties are no longer true, and we'll see what happens shortly. But before that, let's look at some pictures just to get a little bit more intuition for what is going on. So the green line, the green tube that you see in my space-time diagram is sweeping out a time-like world tube that represents the trajectory of whatever source that is producing my phi. And what the Green's function is telling me is that every point in J is producing a signal, in this case in flat space-time, that propagates strictly on the light cone, denoted by the black cone that you're seeing, this cone over here. So the signal that permeates space-time is basically the sum over all the possible cones that emanates from J, from every point in J. if you turn it around and think about what does an observer see, the observer will itself sweep out a time-like world line, and because the signal propagates strictly on the light cone, the observer will see a signal that really comes from the intersection between its own or his or her own parsed light cone intersecting with J, which is this little portion over here. All this is again still in flat space-time. Now let's see what happens when you move on to curved space-time. So I still have a massless scalar, but now the wave operator acting on it is quite a bit more involved, and it would depend on the actual geometry of the space-time that you are interested in. So this G mu nu describes the geometry of the curved space. But conceptually, the Green's function is still the field phi observed at x, produced by a space-time point source at x prime, except now the point source is described by a covariant delta function on the right-hand side. But just as in the flat space case, phi is once again the superposition over all the field produced by all space-time point x prime, weighted by the physical source J, but now you have to do the integral in a space-time covariant manner. So this is where the departure from flat space-time comes in, and this is where Hadamard comes in. So Hadamard showed, although my understanding is it didn't use covariant language, what he showed essentially was that in four-dimensional space-time, if you remain in a region of space-time where the source and observer are linked by unique geodesics, you can show that the Green's function will always split up into two terms. One, this delta function term that you see over here, describing propagation on the light cone. So sigma is essentially the distance, the square of the distance between source and observer. And so delta function says that the distance is zero, namely you have a null propagation. And the stat function here, in my sign convention, tells you that sigma needs to be strictly positive for it to be relevant. So V, the tail function, describes the propagation inside the light cone, the dark gray area that you see in my space-time plot over here. What's also important to recognize is that the character of these two terms in the Green's function. It turns out that the light cone part of the signal, the square root delta that you see here, can be solved once you understand how to solve the null geodesic equation in your relevant space-time. And the null geodesic equation is just describing the idealized limit of a null point particle freely falling in whatever space-time you're in. So there's actually no field, the field in the phi, the field in the field theory is not present until you actually look at the tail function V itself, because it is the tail function V that actually requires the solution, the full solution of the wave equation, the homogeneous wave equation, box V equals to 0, and subject to non-trivial boundary conditions on the light cone. So in particular, you start with the apex or the tip of the light cone over here. And it's possible to show quite generally that for the massless scalar, V has to be basically proportional to the Ricci scalar at the tip. And there are ways to then integrate this condition along the light cone, and then that in turn will serve as boundary conditions for your homogeneous equation. So essentially, if you have non-trivial geometric boundary condition on the light cone, you expect that generically that there ought to be inside the light cone propagation of your field phi, even though it is the particles associated with it are massless. So what I like to highlight is the conceptual point here that really detecting the tail part of the signal in a closed space-time, I would assert is really the way to have a robust test of our understanding of classical field theory in closed space-time. Because again, the null cone part of the signal, it just merely corresponds to the null geodesic equation. It's just freely falling, idealized point particles, and it really doesn't have much of the field content of the field theory. So now let's see how this discussion would have an impact on dynamics of systems in residing in closed space-times. And what I mean by that is the following. Suppose you have a system, a dynamical system, can be a bunch of masses, some stars orbiting around each other, or electromagnetic charges interacting with each other. And the system will sweep out its own world too in whatever closed space-time it's living in. And as we've seen, the signal that these systems will generate in closed space, or I should begin in flat space-time. If you are in flat space-time and you are in 4 dimensions, then the signal will just, as we've seen, propagate strictly on the light cone only. And so your signal will never come back and interact with yourself in the future. But if you are in curved space, then what will happen is that for each point along your own history, you will generate a signal on the light cone, but also a signal inside the light cone, which is this gray region that we see over here. And so from the picture, it's very clear that the signal you generate at a given time would continue to interact with yourself in the future. And this is why I like to call this the tail-induced self-force. And there are exceptions to this rule that I would come to in a little bit, but this would happen generically for both electromagnetic and gravitational radiation. In other words, you would expect both a electromagnetic and gravitational self-force once you're residing in a curved geometry. If you kind of turn this around and ask, at a given event in space-time, if you ask what is the force that you experience, what is the self-force that you would experience at a given time and location, then because you will receive a signal both from your past light cone and from the interior of your past light cone, you see from this picture that you become now sensitive to actually your entire past history, at least in principle. In practice, it would depend on the actual structure of what the tail signal looked like and how strong and how sensitive it is to your past history. So you have to solve it to know how things go for a given space-time. So let me just highlight again the first result, first of such results due to DeWitt and Brownie. And so now we understand that this equation, this term in equation 5.26, integrating over the proper time of the charge from minus infinity to it's the current time, it is in fact corresponding to the integral over the entire past history of the point electric charge. And that's because now electromagnetic radiation, again, develops a tail in curved space. So let's come to gravity itself, but let me talk about it by first referring to the Nobel Prize that was awarded or is going to be awarded this year. Half of the prize, as you guys might know, was awarded to the work that that you see on the screen right here, that used powerful telescopes to peer at the heart of our own galaxy. And what they have shown over the past decades is that looking at the orbits of these objects and the small size of the central mass that is responsible for these orbits, we are able to infer that this is very likely a 4 million solar mass black hole. You don't see it, it's dark, but it's so massive inside such a small volume. What else can it be? And why this is particularly important is because it was the beginning of the astronomers' discovery that other galaxies probably also have their own supermassive black holes residing at their core. So from the gravitational wave perspective, we're hoping by the 2030s to put satellites up into space to look for gravitational waves produced by these systems that you see on the screen here. These are usually called extreme mass ratio in-spiral systems because the compact bodies are usually solar mass of roughly order of solar mass, but the central objects are a million, sometimes even a billion solar masses. So there's an extreme ratio of masses there. But the motion of these bodies near these supermassive black holes would stir up the space-time in that vicinity and produce gravitational waves that would then propagate out to our satellites. And this is the hope is that we would be able to hear these gravitational waves and allow us to, for the first time, directly probe the strong field, the strong gravity regime of these supermassive black holes. The key conceptual issue that needs to be resolved if we want to produce high accuracy predictions of these gravitational waves is that of the tail-induced cell force that I just discussed. So let's see what's going on over here. So in this case, the green tube that you see in the figure is the world line of one of these compact bodies orbiting, let's say, Sagittarius A star, the 4 million solar mass black hole in our own Milky Way galaxy. Now, what happens is the following. If you ignore the tail-induced cell force, then A mu, which is just the covariant acceleration of these objects, would in fact be zero. So that's not surprising. So that's just saying that in the curved space-time, massive bodies would simply free fall and obey a time-like geodesic equation. But because we've just seen that the signal that these bodies would produce have a time-like component, it has a tail component. So what you're seeing over here is work done by a Japanese group as well by the Chicago group, showing that at first order in the mass of the compact body, you in fact receive a correction to geodesic motion coming directly from the tail of the Green's function, interacting with the trajectory of these compact bodies. And the special feature about general relativity is that because general relativity is nonlinear, this answer is actually approximate in the sense that there are higher nonlinear corrections to the cell force equation that our relativity colleagues, in fact, are still working on. So there is a yearly CAPRA meeting where they come together and discuss their latest results. From a field theory perspective, this tells us why it is so important to try to develop a deeper understanding of how of the properties of gravitational Green's functions, especially in black hole spacetimes. It's something that I hope to move my research towards over the next few years. But for now, let's talk about gravitational wave tails. Firstly, in the simpler context of cosmology, which is what I've been working on for the past few years. So, in case there are those who are not familiar, if you look at what's called the tensor polarization of gravitational perturbations in a cosmological geometry, so A here is the relative size of the universe, and chi is the perturbations of the otherwise perfectly homogeneous and isotropic universe containing what we call the gravitational radiation. What you find is that the tensor spin-2 polarizations take on two possible forms. One rotated 45 degrees relative to the other. So what you're seeing here is that if you sprinkle a ring of test masses in space-time or in space and just let them free fall, and if you have one of these gravitational waves pass through these test particles, then this is the oscillatory pattern that they will undergo. But there's more than that. It turns out that gravitational radiation behaves sometimes quite different from the electromagnetic radiation that we are used to. If I turn off the lights, then I don't see a signal anymore. I don't see light anymore. But it turns out that in gravitational radiation, even though the primary wave train could have passed by and died off, it turns out that amplitude does not always return to zero. So this is the comparison between the rate line, the rate wave that you're seeing in this plot versus the blue one. So the rate one returns to zero, but the blue one suffers essentially a DC shift that in the gravitational literature is called memory. And what that means is that if you think about what happens to this ring of test masses, it would oscillate back and forth as the wave goes up and down either in the red or the blue curve. But if it is the blue curve, what will happen is that the ring of particles will no longer return to a circle, but it will actually be permanently distorted depending on the orientation of the polarization. So what I found several years ago was that if I looked at the simplest example of cosmological spacetimes, known as de Sitter space, which is really just a exponentially expanding universe driven by the cosmological constant or something like it, you would find that the Green's function can be solved readily in the space-time. And you'll find that the light cone part actually looks very similar to that in flat space that you saw a few slides earlier, except that now it's rate shifted by these scale factors, A of eta and A of eta prime, where again, A is just the scale factor in this particular de Sitter cosmology. But then you'll see now this explicitly new term compared to flat space, which corresponds to the tail. So the step function here just tells you that inside the light cone, eta minus eta prime, greater than r is the distance between source and observer. Inside the light cone, it turns out to be a space-time constant h squared over 4 pi. And this is, again, to be contrasted against the flat space situation where you expect your waves to always fall off
For
with
your
this,
question, show number.
whereas in if you look at the tail signal in de Sitter, it's just a constant, doesn't fall off with distance, doesn't fall off with increasing time. So let's think about what that means in a hypothetical situation where you place a compact gravitational wave source in de Sitter, and suppose it turns on for a finite duration. This dashed line over here produces gravitational waves, and you put a detector someplace in the distance, and what you will see is that on the null cone, you would receive a signal that falls off with 1 over distance. But then by the time the source has turned off, you would recognize that you would detect that the gravitational waves do not in fact die off to 0, just as the blue curve in this plot goes. But rather in this gray region, inside the light cone of the source, of the radiating source, there will now be a DC shift, a pure constant that basically displaces the metric of the space-time everywhere in this interior. In other words, the space-time constant tail actually gives you a very small but non-trivial gravitational memory everywhere inside the interior of the cone of your whatever gravitational system you're looking at. I should mention this is all in the context of linear gravitational waves. Namely, if you just take the Green's function, convolve it against your mass energy, and this is what you would, this is the picture that you would arrive at. But as we have mentioned before, general relativity is a non-linear theory. And it turns out that even in flat space, it's been known for a long time that the non-linearities of general relativity itself would also generate further memory effects that are in turn sourced by the gravitational energy of the linear gravitational waves themselves. So naturally, there's a question, what then happens in a cosmological context? In particular, what about the tail-induced memory that I found several years ago? Would it receive corrections, for example, once we do include the nonlinear corrections? And so over the past year and a half or so, with my master's student, Afif, and my former postdoc, Yan Wei, we are taking a massless scalar, putting it in a perturbed de Sitter in the sense that we put a central mass in de Sitter so that now it's not pure empty space-time, but there is now a perturbation generated by the central mass. And we now propagate our massless scalar in this perturbed space-time to mimic a scalar-scalar gravity 3-point interaction. so as to see what happens to this scalar memory as it propagates forward in time. This is supposed to be a toy or warm-up to the full gravitational calculation, which I expect to be much more complicated. And that's why we're starting with just a scalar field, just a massless scalar field in perturbed de Sitter for now. And in fact, what we have found is that we're now quite close to completion, and we have found not just the linear memory that I found in the gravitational context, but we have actually found indeed that the first nonlinear correction does also have a very similar space-time constant gravitational gravitational-like, I should say, DC shift. And if you dig through the literature, actually the numerical relativists have gotten there quite a number of years ago, except they didn't quite call it gravitational memory. What they did was, or scalar memory, actually, in this case, what they did was to take the same scalar field that I'm talking about, but evolve it in an exact Schwarzschild or Reisner-Nordstrom de Sitter background. And what they found was that the monopole moment of the field, which is exactly this space-time constant DC shift that I'm discussing here, in fact, remains non-zero in the late time limit. And so we have what Afif and I and Yanwei have done is essentially we've developed analytic perturbative methods to complement what these numerical relativists have managed to do. And not only that, we have actually figured out how to compute the nonlinear corrections to what they have done. Before I move on, let me also mention that in de Sitter, there is a different way of looking at the tail effect but by actually recognizing that de Sitter can be viewed as a hyperboloid situated in a one higher dimensional flat space-time. So this is the hyperboloid that you're looking at. This is de Sitter space, but living in one higher dimensional flat space. These black lines that you see are the light cone of the Green's function if you put this point source at the tip of this pink line. And these wavy lines that you see are actually the equipotential lines of the tail of the Green's function. So this is from the intrinsic perspective. If you're living on the hyperboloid, that's what the Green's function would look like to you. But you can also think of it from the ambient flat space-time perspective. And what it turns out is that you can cook up the right charge density, which is this line that you see over here, that pierces the hyperboloid in such a way with the right charge density that generates the same Green's function on the hyperboloid, but from this ambient high dimensional perspective. I'm not going to go through the details, but let me just say that the tail in particular comes from recognizing that each point on this charge produces its own signal. You're in flat space, so all you have to do is just draw a cone, and you see that will intersect exactly these equipotential lines on the hyperboloid. And so the sum over all these signals is in fact the tail signal on the hyperboloid itself. There is a question of whether is it possible to extend this technique to other space-times, particularly black hole space-times. But now let me move on to electromagnetic radiation, still in cosmology. This goes back to work that I started with Glenn when I was still a PhD student here at Case. And the basic question here is whether we understand from first principles how light propagates through our universe after it became transparent, meaning below a redshift of roughly 1,000. It turns out that Maxwell's equations are completely insensitive to the scale factor that shows up in the geometry of a perfectly isotropic and homogeneous universe. So right away, you can tell that the flat space solution, in fact, carries over directly to the cosmological solution for Maxwell's equations. So this is an exception to the discussion of tails that we had at the very beginning of my talk. So there are no tails for electromagnetic radiation if you are in a perfectly homogeneous and isotropic universe. But of course, that's not quite the universe that we live in. The universe that we live in has structure, has galaxies, it has large-scale structure. And so there is some perturbation that I described with H mu over here. And once you have perturbations, then Maxwell's equations become like Maxwell's equation in cosmology, become like that in perturbed Minkowski, in perturbed flat space. And now there's a question of what kind of tails would you generate once you turn on these clumpiness due to dark matter. And so what Glenn and I figured out was how to carry out perturbation theory on the Green's functions themselves. And without going into the details, let me just point out that at first order in the perturbations, so once you turn on the perturbations, you would in fact discover that you get a non-trivial step function term that indicates that you get inside the light cone propagation of light. So what does that mean? Without caring about the detailed math of it, what it means physically is that if you start from the source of the Green's function, at first order in perturbation theory, the light would try its best to still propagate on a null geodesic. But because of the inhomogeneities in the cosmology, it would now scatter off these inhomogeneities. At first order, it would scatter once, and then it would take a return null path to the observer. And if you ask at a fixed elapsed time t minus t prime, what is the locus of all points where you will receive such a signal? It turns out to be this ellipsoid that whose foci are simply the observer and the source of the Green's function. So conceptually, we're used to thinking about the cosmic microwave background as emanating from a large scattering surface. There's a thin shell where we're sitting at the center, whose radius is, roughly speaking, the age of the universe, because that's how long, very roughly speaking, it took to reach us. But if you believe the calculation that Glenn and I did, then what we're saying is that, in fact, there's a little bit of a light that propagates inside the light cone, and therefore it's actually not the large scattering surface anymore. There's actually an interior of the sphere that we also receive a signal, probably very weak, but still non-zero. So it turns out the technology that we developed for this project is in fact directly relevant to the weak field version of the Embry system I described at the very beginning to motivate the tail-induced cell force. So if you consider, say, a compact star orbiting a much larger central mass, then what you discover is that in this weak field system, the tail signal consists of the signal that's generated by this orbiter that then interacts with both the gravitational potential of the central mass and with the mass distribution of the central mass itself. And this scattering off the potential and the mass then gives rise to the tail signal that comes back to hit the orbiter and produces a self force. And this is where Claudia and Glenn comes in again. We followed up with this calculation of a central of an orbiter undergoing circular motion, and we in fact discovered that this tail, the scattering phenomenon responsible for the tail, which is what this diagram is saying over here. So this line is the compact body. The thicker gray line is the central mass, and what is filling the interior of the lightcone over here is really a continuous scattering where every part of the compact body is producing a signal, and at first order will scatter off the potential and the central mass, producing this tail-induced self force. So we did it for both the E&M and the gravitational case. I'm showing only the E&M result. Zeta, in fact, is the ratio of the size of the central mass divided by the distance between the orbiter and the central mass. And so what this seems to be telling us is the self force, this tail-induced self force, appears to be sensitive to internal structure of the central mass. And it could potentially be very interesting if we can build detectors sensitive enough to measure this component accurately. I also want to make an advertisement for work that Claudia, Craig, and Glenn did recently. I think they went on to look at not just the self force that is exerted on the orbiter, but also what happens when radiation scatters off a perturbed space-time like that. And what they found was that scattering off the central mass does produce the sizable signal. So if you're interested, go talk to them. Let me move on to odd dimensional flat space, where you would also have a tail, even though now you are in zero space-time curvature. This is something that is not well appreciated, and I guess rightly so, because we live in 4 dimensions. But what I'm going to try to show is using what Hadamard calls his method of descent, and using the fact that we know in 4 dimensions light and gravitational waves propagate strictly on the light cone. I should mention before we go there that conceptually speaking, why tails develop in odd dimensions, I believe, has to do with the fact that it's not possible to construct a perfectly spherical wave that propagates strictly on the light cone. Because sometimes I get this question, well, I can write down the plane wave that propagates on the light cone, just write down e to the minus ik dot x. What's wrong with that? But here, geometry plays a crucial role. Let me just skip ahead to do it because I think I'm running short of time. So the key observation that we want to know is that you can imagine if you are in 3-dimensional space-time, meaning 2 space and 1 time dimension, you can imagine that that is a space-time that is actually secretly living in 4-dimensional space, but with the observer confined on this plane that you are seeing here, the blue plane that you're seeing here. So what I'm doing also is I'm taking a snapshot of space. So this is not a space-time diagram, but a snapshot of space at a given instant. So let's see what happens. If I turn on a point source on this blue plane, by translational invariance, it turns out that from the ambient 3+1 dimensional perspective, the point source responsible for my Green's function actually is a line source that is piercing the world that I live in perpendicularly. And if you take that into account, you can now use the fact that light and gravitational waves propagate strictly on the light cone to figure out why there must be tails in one lower dimension, namely in 2+1 dimensions. So here we go. So if you turn on the source at x prime not g prime really, then as you progress in time, you would draw a sphere around yourself, the observer at x, of radius equals to the elapsed time, because light or massless particles do travel strictly on the light cone, and that's the light cone in space. If your elapsed time is less than the distance between you, the observer, and the source, then obviously you don't get a signal. The first signal that you get is when the elapsed time is exactly the distance, the shortest distance between you and the line source at x prime, and that is the signal on the light cone from your intrinsic 2+1 perspective. But as you go beyond that, as the elapsed time goes beyond the distance between x and x prime, you will see that there will still be an intersection between the light cone, which is this thin sphere, and the line source that pierces the plane from the 3+1 dimensional perspective. And it's this intersection that tells you that you will always continue to receive a signal from the source, even though now you are inside the light cone. And this is exactly from the 2+1 perspective, the tail signal. So you can work it out and show that this embedding perspective allows you to derive a recursion relation that lets you derive the d+2 dimensional Green's function from the d-dimensional guy just from differentiation. And why I mention this is because once you've gotten the 3-dimensional Green's function, you can use this recursion relation and obtain all the odd dimensional Green's functions. And because the 2+1 has a tail, in fact, it's a pure tail, all odd dimensional Green's functions have tails. And what I'm showing over here is, in fact, the gravitational wave signal, the linear gravitational wave signal generated by an arbitrary stress tensor T mu nu. But now you see in odd dimensional flat space time, you again need to integrate over the entire past history of the source to understand what is the cumulative signal. It turns out that this history dependence is complicated enough that if you dig through the literature, you'll find that, in fact, the quadruple radiation formula that we know so well in 4 dimensions has only been derived using quantum field theory methods and only in frequency space. So with my new grad student, I'm trying to, in fact, revisit this problem since it's such a fundamental formula, but try to do it using purely classical methods and also in position space to try to gain some insight into what properties of the waves do we really understand, and from what portion of the history are the signals dominated by. So I hope I can go on for a few more minutes, and this is so. Let me finish with the last topic, which pertains to the quantum field theory of photons and gravitons, but in flat space-time. This topic falls under the name of microcausality, and let me just focus on free photons in 4 dimensions for the time being, even though the gravitational case is very similar. So it turns out that if you ignore any charged currents that may be present and just focus on the electromagnetic field itself, at the level of the quantum field theory, you would discover that it is the transverse part of the spatial components of the vector potential that needs to be quantized. And that's because it's the transverse part that actually obeys a wave equation that you see over here. The other portion, in fact, obeys a Poisson equation. And if you are in empty space, this portion is just 0. But because this is transverse, which means if you take the divergence of this as 0, it turns out to give you a non-local projection in position space. If you flip open Pascal and Schroeder, it would tell you that the propagation of particles in quantum field theory can in fact be space-like, meaning if you start from y and you ask what's the amplitude that your scalar particle in this case can propagate outside the light cone of y, it turns out to be non-zero. But as they explain in this paragraph, that what we should really be bothered about is whether they are compatible observables, even if they are outside each other's light cone. So if phi of x and phi of y do commute outside the light cone, then all is well, because that means that you cannot make an observation of phi outside the light cone of y in such a way that you can affect the observations. But this, as I'll explain, appears to break down for free photons. If you sit down and spend maybe a couple of days, work out all these crazy Fourier integrals, you would discover that the Green's function for these transverse photons, in fact, have a non-zero portion outside the light cone of the source. So if you work out the commutator, just as Pascal and Schroeder tells us to do, you would discover that, in fact, whatever they're saying over here fails to go through for the very important case of photons. So what I'm trying to do at this point is to understand, is this something that one should be bothered about? And if so, what kind of physical implications would it provide? I did a bit of digging and found that the condensed matter people who are interested in, I think, quantum optics have already been writing papers on spatial localization of photons. And what they tell us, this paper in particular by this Polish authors, is that it's possible to construct one particle photon states where the correlation functions of the electric field is localized, very sharply localized, in the sense that as long as the photon state is not is zero outside the point where you're evaluating your electric field, then you can show that the expectation value in that state is essentially just the same as you if you were just computing the same correlator in vacuum. But if you can do it for electric fields, but simultaneously you will find that this locality would break down for magnetic fields. And they go on to claim that vice versa. So if you can localize it for the magnetic fields, you will not be able to simultaneously localize it for the electric field correlators. So what I have checked is that this property of non-localizability is in fact related to the divergence-free property of the photon operator, which, as you may recall, is related directly to this violation of microcausality. But I do need to work on it a little bit more, mull over it a bit more, and many issues remain to be understood. So hopefully, uh, in the not too distant future, I'll get to visit Case in person and tell you more about this line of work. And thank you for listening.
Okay, thank you. Right, so we have time for questions. You can either unmute yourself and ask the question or type into the chat. So you want to ask?
Yeah, thanks for the very interesting talk. So I have a, I'm wondering if it may not be that relevant, but is it possible that DC current is related to a geometric phase in some way?
We're talking about Barry's phase.
Yeah.
Yeah, I've not thought about it, but it's an interesting question. So the thing is that there's no closed path here, right? I think you're talking about a memory effect that I found induced by the tail of the gravitational wave.
Yeah.
Is that correct? Is that
Yeah,
what you're
yeah.
referring to? The
Yeah.
memory effect.
Yeah.
Yeah. So in this case, there's no closed path that you need to take, which happens in the Barry space. But who knows? Maybe there's a quantum mechanical interpretation of this memory effect. It might be worth thinking about.
Thanks.
Any other questions?
I have a question.
Yeah.
Yeah.
Can you hear me?
Yes, go ahead.
Okay, so hi, Yi-Zen.
How are you doing, Claudia?
Very nice. So I heard an interview yesterday from Andrea Guess, and she was claiming that because she's studying these, like, small bodies orbiting, like, supermassive black holes at the center of our galaxy. Can you hear me?
Yes, yes. Now I can.
Claudia, did we lose you?
Yeah, I think I lost her on my end.
Yeah, here too. How do you maybe type into the chat?
Okay, we'll see if she reappears. Any other questions from students in the meantime? So Harsh, do you want to ask your question?
Sorry, I'm back.
There's Claudia.
Because the signal is not very good. But so yeah, I was watching an interview yesterday from Andrea Guess, because she's studying exactly this type of systems, and she's claiming that basically soon she's gonna publish a paper, because it seems that they can actually tell, using these systems, you can even detect if there are like tiny amounts of dark matter that actually affect the orbital evolution. Like, do you know more about this?
I've heard about. I've seen papers. People thinking about whether dark matter affects these Embry systems, but I haven't looked at it in great detail.
Because I was surprised when I heard it, because I thought that the dark matter effects, would be relevant maybe for some other systems, but not for the EMRIs. Because she was saying that she can tell that because it seems that, like, without dark matter, like, the system should have like a certain evolution, so you can calculate coefficients and stuff. But if there is an additional thing going on in your system, then basically the orbital motion can change. So I don't know.
We do expect dark matter to accrete on the central supermassive black hole, right? there should be non-trivial accretion. So I wouldn't be surprised if there is some effect.
There'd be a non-trivial mass distribution around the black hole. So
Yeah,
Yeah.
yeah.
does that mean you might be able to detect the tail effects
I
There should
think
of the structure of the mass distribution?
Yeah, there should be a modification, right? Because even without dark matter, there is already a tail effect. So there will be a
Right.
modification to the tail effect if you also have a non-trivial mass distribution.
that's right. I mean, like, you know, if general relativity is the correct theory of gravity anyways, like we
Mhm.
expect that basically we should see tails at some point. I
That's
mean,
right.
I don't know when, but
Yeah.
I mean, it's a prediction of the theory itself. So,
That's right.
I mean, another question that I had was related to this causality concept,
Uh-huh.
because I would have thought that, you know, propagation outside of the light cone actually implies causality, or at least certain people try to prove that.
Why do you say that? It implies causality.
It implies, sorry, acausality, propagation outside the light cone.
Yeah. And usually people say
So-
that's why you need antiparticles, right? You need antiparticles. The commutator that respects microcausality receives contribution from both the particle amplitude and the antiparticle amplitude, and the interpretation is that they cancel each other out outside the light cone.
Yes, but I thought that, I mean, it depends on what you mean by microcausality, because I guess like you can be careful there and like invent all sorts of definitions about causality.
Yeah, I thought the basic definition is just that the commutator needs to vanish outside the light
Because
cone.
this is what I thought, that for example, the tails would have only support from the interior of the light cone, not outside the light cone. That contribution.
Yeah,
would
I don't
be
know what to
zero.
call this one, but that's why I think I didn't quite call it a tail, but yeah, I don't know what to call it.
So it's not the tail.
I at some point it's semantics, right? It is at some level it's just semantics, but call it what you want, but it is non-zero, right? This blue.
But this is the thing, but it's not a tail. I mean, okay, semantics might, but I
Yeah.
want to stress that out because it's not a tail, I think. It might be something else, but it's not.
Okay, I'll cook up a different name for it, but
Sure.
as you can see, is non-zero. There's T over R with the derivatives acting on it.
So you're finding this in the correlator of like the transverse part of the photons, but in a quantum field theory, shouldn't we expect microcausality only to hold for gauge invariant local operators? And this isn't really a local operator.
Yeah, so I think that might be the issue, right? Which is that it is not local, but are there so I think what you're saying is that there's no local at the level of the fields. The photon operator is just not local, right? So maybe
Well,
we should.
yeah, A itself is not a gauge invariant. The transverse part is, but it's not local.
Right.
But if you looked at the E and the B fields, this shouldn't be there. Is that true?
That is correct. Yeah. So if you just check the curl on both sides, it won't be zero. So in fact, you see
Right,
this
yeah.
this derivative structure will kill itself once you take the curl.
Right.
Yeah. But let me ask you, because maybe you know a bit more about this. If you do ask the question, right, what creates the photon? Is this operator that you will act on the vacuum, right, and then convolve against some wave packet to
Well,
create the most general
Well,
state?
I'd say it's really F mu nu. That's the true gauge invariant local operator in the theory.
But that would be the electric field, right?
Yeah. But that's the true local operator.
How would you calculate, for example, the amplitude of, creating a photon in X and then propagating to Y, for example? For the scalar field, it would just be the Whiteman function, isn't that right?
Yeah, it should be just the 2-point function of two Fs. It should be embedded in there. But maybe we should discuss this afterwards since it's
Sure.
more technical. Harsh, did you have a more general question?
Sure, I can ask a general question. So I was wondering if you could give us some intuition why this tail effect would be more pronounced when you're looking at the spiral of, in an extremal situation where you have a supermassive black hole and something falling into it, as opposed to something like LIGO, where you have more or less symmetrical, equally heavy things colliding.
Right. So the equal mass, I think I would say that it's harder to disentangle the tail part, because if you have an equal or comparable mass binary system, the whole thing is just very non-linear, right? And so what you call, particularly in the strong field regime, what you call the tail and the light cone, I think, becomes much more entangled. So we're not saying that or I'm not saying that it's not there, but rather it's just harder to disentangle. You put it all on the computer, right? The actual modeling of the comparable mass system. Nowadays, people just put it on the computer.
Yeah. Well, there's that early in spiral, which can be quite long in some cases, and
yeah, then that would be the post-Newtonian regime, which is partly related to what I was talking about when we computed these cell forces. Yeah, that is in fact the motivation.
Yeah.
Yeah. Yeah. So this is so when you have, so we did assume in this paper that the central mass was heavier, but in principle you can have the same weak field methods can also apply for the comparable mass situation. Yeah.
Joel. Sorry, I had a question.
Go ahead.
If the thing that's breaking conformal invariance is chiral, would that lead to, for example, chiral tails?
I see what you're saying. Yeah, I think so. You might have, you're saying that somehow left circularly versus right circularly light might develop different tails, right? Yeah, it's possible. Yeah, if you break the symmetry. Yeah.
Yeah, and so there are like other effects which also lead to deviation from a null geodesic. For light, for example, you have like the gravitational spin Hall effect. So how would you distinguish that from a tail?
Do you still propagate on the light cone though, if you do spin Hall?
I'm not sure about that.
Yeah,
but I do know that it deviates from the null geodesic.
It's not just that you are modifying the polarization. I probably need to look into it, but I'm not. You're not just modifying the polarization of light, but you're saying that it actually travels slower.
In the tail case?
No, the spin Hall.
Well, I'm not sure it would travel slower.
Yeah, because that would be the distinguishing feature, right? What I am saying is that in a curved space-time, the photon itself would in fact travel slower than unit speed. That's the mark of the tail effect. Yeah.
Oh, I see.
Yeah.
Thank you.
And isn't important, they travel at all speeds. They don't
right.
just follow this, they won't even follow a different geodesic.
That's right. Yeah. It's not like it becomes time-like, right? It's not a time-like geodesic. It kind of fills the generically it fills the interior of the light cone. Yeah.
Thank you.
Okay, if there's no further questions, maybe this is a good time to end the recorded part, and we can stay after if anyone's interested in talking with Yi-Zen a little more. So let's thank Yi-Zen again.
Thank you. Thanks for